Just look around you. You see a solid world, right? There are tables, chairs, your own hands. They exist. They're in a specific place. It's just common sense. But what if I told you that deep down, on the tiniest scales you can imagine, none of that is really true? What if the very foundation of our solid, predictable world is built on a set of rules that just defy all logic? Let's dig into that.
See, all of our intuition, everything we think we know, it's built for a world of big things. We're talking billions and billions of atoms all clumped together. But the moment you zoom way in, way in, on just one of those atoms, a single electron, the whole game changes. The rules just go right out the window.
So, that's the big question, isn't it? This is the question that completely shattered physics. It's a journey into a world that doesn't just mess with our senses, but with the very meaning of words we take for granted. Words like path, or position, or even what it means for something to be.
Okay, so to get started, we are going to have to break down our most basic assumptions about how things work. And we're going to do it with a really simple experiment that has a profoundly strange twist at the end.
Okay, just imagine you're throwing tennis balls at a wall that has two doorways in it. Simple enough. Each ball is going to go through one door or the other, and it's going to hit the back wall, leaving a mark. After you've thrown, say, 1,000 of them, you'd expect to see two nice, neat clusters of marks right behind each doorway. Makes perfect sense. It's predictable, it's logical.
But this is where reality starts to fall apart. When we switch out those tennis balls for tiny little electrons, the result just makes no sense at all. Instead of two simple clusters, we get this zebra stripe pattern. This is an interference pattern. It's the kind of thing you'd expect to see from waves crossing each other in a pond, not from solid little particles.
And here is the paradox that will bake your noodle. Every single electron arrives at the detector as a single click, a whole individual lump, just like a particle should. We never, ever get half a click. But the pattern they build up over time, it looks exactly like a wave interfering with itself. So, which is it? Is it a particle? Is it a wave? What is going on?
I mean, this is baffling stuff. So naturally, scientists wanted a peek behind the curtain. If the electron is somehow acting like a wave, how is it doing that? The logical next step was to just, try and watch it in the act.
The logic here is super simple. If each electron is interfering with itself, maybe it's splitting in two, going through both slits at once and then recombining. So hey, let's just put a tiny little detector right at the slits to see which path each electron actually takes. Should be easy enough, right?
Okay, so just to remind ourselves, this is the bizarre wave-like pattern we get when we are not looking. Each electron somehow seems to know that both slits are there, even when we send them through one at a time.
And what happens next? Well, this is the central shock of all of quantum mechanics. The very moment we watch to see which slit the electron goes through, the interference pattern vanishes. It just disappears completely. And what are we left with? Two simple clusters, exactly like the tennis balls. The very act of observing changes the result. This leads to a conclusion that is just staggering. It's not that we don't know the answer, it's that the question, which slit did it go through, might be a meaningless question to ask. In the quantum world, before we measure it, a particle might not have a definite path. Our common sense words, they just don't work here.
So if our intuition is totally useless, how do physicists predict anything? Well, they had to invent a whole new set of rules for reality itself. And the way they did it is both incredibly bizarre and beautifully simple.
Instead of trying to predict what will happen, we calculate the chances of what might happen. And we do it with something that sounds almost like a kid's game, little arrows. For every single possible way an event can happen, we draw an arrow.
The real magic is in how you combine these arrows. You draw an arrow for every single path the electron could possibly take. Then, you add them all up, head to tail. Now, if two arrows point in the same direction, they build on each other and create a big final arrow. That means a high probability. But if they point in opposite directions, they can cancel each other out completely, and the final probability is 0. And that right there, that's interference. That's why we get the zebra stripes.
Okay, so this slide basically sums up the one rule that governs this entire strange world. If the different ways something can happen are fundamentally indistinguishable, like an unwatched electron going through either slit, you add the arrows and bam, you get interference.
But the moment the alternatives become distinguishable, even just in principle, you just add the probabilities like normal. No arrows, no interference. That's it. That's the rule. Now, I know you might be thinking this is all just weird, abstract stuff that only physicists care about. But these bizarre rules are the reason the world you're in right now is solid and colorful and, exists at all.
No, really, this isn't some theoretical curiosity. The solidity of your chair, the light from the sun, the very chemistry that makes you, you, it is all governed by these strange quantum laws. Let's take a quick look at how.
Now, this isn't about having bad measuring tools. It's a fundamental property of nature itself. A particle simply doesn't have a precise position and a precise momentum, which is basically its motion, its oomph, at the same time. The more you try to squeeze an electron to pin down its position, the more wildly its motion fluctuates. And that furious pushback, that's what we feel as solidness. It's what keeps atoms from collapsing on themselves, and what keeps you from falling straight through the floor.
In our world, energy seems smooth, continuous. You can give a car any amount of speed. But inside an atom, an electron can only have specific, allowed energy levels. It's like a staircase, not a ramp. And when it jumps from a high step down to a low one, it spits out a photon of light with a very, very specific color. These are the unique fingerprints that tell us what distant stars are made of, and it's the exact same principle that powers every laser, LED, and computer chip in the world. And this might be the most consequential one of all. For some reason we don't understand, electrons are just antisocial. They absolutely refuse to crowd into the same low-energy state. This forces them to occupy different levels, building up shells around the atom. Now, this isn't just some quirky habit. It is the sole reason we have the periodic table and all the rich, wonderful variety of chemistry. Without it, all matter would just collapse into a featureless, boring soup. There would be no structure, no complexity, no life.
So we've seen how nature behaves. We have the rules. They're incredibly strange, but they work flawlessly. But that leaves us with one final haunting question, doesn't it? But before we get to the philosophy, let's be absolutely clear about one thing. This theory is outrageously successful. The predictions of quantum mechanics match what we see in experiments with an accuracy of up to 10 decimal places. To put that in perspective, that's like measuring the distance between New York and Los Angeles and getting it right to the width of a single human hair. It's staggering. We may not understand the deep why behind any of these rules. Why do electrons refuse to share a state? Why does just looking at something change reality? We have no idea. But what we do have is a set of instructions that, when we follow them, perfectly predict the outcome of any experiment we can dream up. And they have never, ever been wrong.
So we're left with this beautiful, strange, and absolutely wonderful picture of the universe. Maybe the real quest isn't to try and force nature to fit into our little common sense boxes of reality. Maybe the real adventure is letting go of our intuitions and simply asking nature, okay, how do you work? And when we do that, we find a world that is far more creative and imaginative than we ever could have dreamed up on our own. And that's a pretty amazing reality to live in.